Our senior design project is the gesture-controlled electric wheelchair. Our solution provides a cheaper and stress-free controlled wheelchair for those who suffer from osteoarthritis. We eliminate a joystick by implementing a glove feature that allows directional movement at the bend of a finger. The glove reads influx sensor inputs, sends them over Bluetooth to the motor controller, which then commands the motors.
We added 2 brushless DC motors to replace the back wheels of the wheelchair. These wheels have integrated Hall sensors to provide feedback to the control system. 3-phase gate drivers were used to output the commutation sequence to the MOSFETs after the PWM signals are inputted. The motor controller is powered by 3 12-volt batteries. The buck converter is used to step down the 36 volts to 5 volts to supply power to the PCB. The high side and low side MOSFETs were used to create a 3-phase power converter. Each BLDC motor has its own printed circuit board. The PCB includes the DRV8323R gate driver, the 6 high side and low side MOSFETs, as well as a connection to the Hall sensors.
The circuit box provides housing for the 3 12-volt batteries, the motor controller PCBs, and the microcontroller. The emergency stop switch is placed at the front of the box next to the charging port. The motor wires are connected to the PCBs through the back of the box using plastic tubing. To eliminate vibrations, the 3D printed brackets were used to mount the components within the box and mount the box to the wheelchair. Here are the 3D printed parts modeled in SOLIDWORKS. This is the hub motor bracket used to connect the motors to the chair. These are the 3 brackets used to connect the circuit box to the undercarriage of the wheelchair.
The glove is powered by a 3.7 lithium-ion battery, which is converted to 3.3 volts using a linear regulator. The 3 flex sensors connect to the glove PCB with the Atmega 328PB microcontroller and the HC05 Bluetooth module. The glove communicates to the motor controller using Bluetooth. An active mode button located on the PCB is used to turn commanding on and off and allow the user to bend the glove without moving the wheelchair.
The glove is embedded with 3 flex sensors, which are used to dictate specific commands. The directions are as follows: forward, right, left, forward left, backwards. We see that the wheelchair meets the weight requirement and supports the weight of an average white male. Now let's look at the wheelchair in action. First we can see the wheelchair moving forward, and then we can see it moving backwards. Next we can see the tight left turn on the left command, and a wider turn on the left and forward command. Similarly with the right, we have a wider turn on the right forward command, and a sharp turn on the right command.
After operating the wheelchair for an extended period of time, we measured the temperature of the gate driver and the MOSFETs. The gate driver's temperature measured 45 degrees Celsius and the MOSFETs measured 37 degrees Celsius.
Here we use a 120 volt battery charger that connects to the 3 12-volt batteries. The wheelchair has an expected operation distance of at least 2 miles. We use a 3.7 lithium-ion battery charger to charge the glove battery. The glove battery expected life is at least 6 hours of continuous use. This meets the requirements and prior calculations. The Bluetooth communication devices had no latency or connection issues during the testing period.
Here is our division of work. Project lead is Simon, hardware lead is Simon, with deputy lead as Mike, software lead as Brianna, with deputy lead as Simon, documentation and testing lead is Franz, with deputy lead as Mike, research lead as Mike, with deputy lead as Franz.
Thanks for watching!